So, good afternoon, everyone. Now, I normally start to fall asleep on a Friday afternoon, so I'll try and stay awake, and I really appreciate you bearing with me. So, these are three of the greatest men in computing. They should be household names, but they're not. And they're three of the people that have inspired me through my journey. Does anyone want to hazard a guess who they are or what they did? Do we have any Polish speakers in the audience? No? No? No one speaks Polish? One. Okay. They are. Well done. Exactly. So I'll come back to these three guys in a second. But let me introduce myself. So as Simon was saying, my name's Doug. I have what I think is one of the coolest jobs in the world. So I get to sit down, design, and implement some of the coolest algorithms for detecting spam and preventing it from going to your inbox, and doing things like filtering out which mail should be important from which mail should not be important. So I work for Google as an engineer. I'm a self-confessed code monkey, and I love it. What I really love about it is that when I write a line of code, it gets executed billions and billions of times a day, and it affects millions of people, even if they don't know it. That's fine. That's great. What I really love doing in my spare time is trying to encourage kids to take a similar path, to experience that, to really get to know the fundamentals of computer science, understand the challenges, and become the next generation of engineers. So, our three heroes were credited with saving 338,000 people from the shores of Dunkirk, where they would have been killed or captured. That's one of the very first ways that decrypting the Enigma machine, the so-called ultra traffic, changed the course of World War II. And it's been said many times that having the ability to decrypt the Enigma machine shortened World War II by 2 years. How's that for impact as far as technology goes? It doesn't get much better than that. So, can you pronounce their names? Yeah. That's better than I could have done. So this guy is Ryusuke, and he in particular was credited with the initial discovery. He reverse engineered the wiring of the Enigma machine, which was a key contribution. But what a lot of people don't realize is that all of this happened way before World War II even began. So here is the patent for the Enigma machine. And it was filed, it was awarded in 1928, and it was filed in 1923. So the Enigma machine was actually in use as a commercial encryption machine for a long time before World War II. So the German military, what they did is they beefed it up. They made it a bit stronger. And the story goes something like this. So Marian Ryusuke and his colleagues were studying mathematics at the University of Poznan in the late 1920s. And because of their background in German and because of their mathematical abilities, they were sucked off by the Polish Cipher Bureau into a secret cipher course at the university, at a military institution near the university. So they studied mathematics in the day, and at night time they went and studied this crypto course. And at the end of this crypto course, they started working with the Polish Cipher Bureau, and their first assignment was to take this German military code, not the Enigma machine, a separate four-letter code, and try and break it. And they did, and they did this very quickly. And as a result, they were so impressed, they gave Marian the job of decrypting this brand new German military Enigma machine. They'd already figured out how to decrypt the commercial Enigma machine, but the German military had beefed up the security by adding extra combinations, this plug board at the front of the machine. So what Marian did is he observed that there were procedural errors in the way that the Germans were using the machine. So the key error, the key to allowing him to reverse engineer the wiring of this machine, was that the Germans sent the first three letters twice. So they would encrypt the initial key positions, the initial rotor positions, and they'd send this twice to, it's a kind of an error correcting thing. They wanted to tell if the initial key positions were wrong. But this was fatal, because it means you get two copies of the same characters encoded twice. And that means you can start to exploit the statistical analysis of it. Okay, so they had broken the German military Enigma machine in 1932. It wasn't until 5 weeks before Germany invaded Poland in 1939 that the Poles realized that it was dangerous for only them to have this knowledge, and they gave it to the Allies. And the Allies went on and spent the duration of the war decrypting more and more sophisticated versions of this machine, hence altering the course of the war. And there are so many wonderful stories, personal stories about the Enigma machine. And there's also so much that's still shrouded in mystery and not really known. I just love the story behind this. So let's say you don't know anything about the wiring of the Enigma machine. You sort of know the rough makeup. There are maybe 10 to the 114 combinations, or the size of the key space is 10 to 114. So that's made up of all the maze of wires and all the ways you can move these rotors and all the ways you can change these plugs and the different rotors you can have. So if you could process 1 trillion, if you could try 1 trillion keys per second, you've got 10 to the 93 years to go through all of them. And we just can't think of numbers that big. But if you know the wiring, which is what Marian Rejewski did, you can take that down to 3,170 years. Okay, well, at least we sort of know that's a long time. But further procedural errors let them even further reduce the search space, and they got it to the point where they could crack this machine in 2 hours. One example of another procedural error was that the German High Command said you should never use the same key twice on consecutive days. That's stupid. I mean, the thing about encryption, the way to get perfect encryption is to make everything perfectly random. If you start introducing rules, it's not random. Another mistake. So the operators had some discretion about how they initially positioned these wheels. And I said that the first 3 letters were sent twice. Well, this was what made up the first 3 letters, the initial positions here. But they could choose which letters they sent, which initial positions. So half of them would just choose QWE, or the initials of their girlfriend or wife or something like that. And the Polish cryptographers figured this out. And they also developed this wonderful thing called a bomber. It's essentially a mechanical version of the Enigma machine, and they had a whole bunch of these in parallel. So maybe we've got our first parallel computing, I don't know. They could actually process a lot of different combinations very quickly. Okay. So what have we learned about? We've learned about codes, we've learned about circuits, combinatorics, search bases, base 2, information theory. What do I mean about circuits? Well, we can actually play with the Enigma machine, and it's a remarkably simple device, right? So I said that the first 3 letters that you send are kind of the initial wheel positions, so I can set some wheel positions. I can move some plugs around to swap some letters, and then I'm ready to type my message. Okay, so I just encrypted a message. One of the key things about the Enigma machine compared to previous crypto schemes is that when you type the same letter twice, LL, it comes out as different letters here. So this is part of what makes it so difficult. It's not just a simple permutation of letters. But how does it work? It's actually super simple. You press a button on the keyboard, and it sets up an electrical circuit through each wheel. And each wheel is a maze of wires. This is what Rejewski figured out. But essentially, it's just a torch. You press a button, it lights up a lamp. And the way it works is mechanically, every time I hit a key, it shifts the rotors just like a counter. So it's actually a mechanical device. And to reverse the encryption at the other end, the whole thing is symmetrical, which is a very important property, because as soon as I type in the encoded message, I get back the plain text. Okay. So we've learned a lot already. So I mentioned that the heart of cryptography is randomness. If we want perfect cryptography, we need perfect randomness. This is really interesting to me because although Tony is absolutely right, it's almost impossible to predict the outcome of a complex program. On the other hand, we actually build computers to be as deterministic as possible. We don't want them to be random. Sometimes they behave randomly, but we don't want them to be random. So computers actually really suck at generating random numbers. And it's a really interesting technical problem, how to generate random numbers. So people, they try and use microphones to listen to white noise, and they listen to rain, they have Geiger counters. They even have cameras pointing at lava lamps to try and generate random numbers. And in fact, in reality, one of the best ways to generate random numbers is to plug in a little dongle that has a resistor, and the thermal noise in a resistor is a good way to generate randomness. So actually, we have pretty good random numbers. So how do you do perfect encryption if you have perfect random numbers? It might sound like it should be complicated, but I have worksheets here that will allow you to do this with a class in about half an hour. And to try and give you an idea, you get your class to generate a random sequence of ones and zeros. Toss a coin, give them all coins, toss lots of them, write down the results, head, tails, 1, 0, 1, 0, whatever you like. Get them to create a message that they want to encrypt in plain text as a group, maybe 10 people. And I've done this with a lot of classes. So I've been to a lot of classrooms and taught this, and they get it. It actually works. So each student can be responsible for encrypting 2 letters. So you write your letters here. You have this table, so you can convert the letters into a binary sequence. So you write out your binary sequence here. So each student is responsible for 10 binary digits. And you get the same student to generate their 10 random numbers, part of the key. So this is going to be the key, which they've done by tossing the coin. And then they do this encryption step, which is a simple exclusive OR function. So the exclusive OR function is kind of magic, because it allows you to mix a random sequence of ones and zeros with a message and perfectly encrypt it. So that if no one knows your random sequence, and if you only use that random sequence once, a so-called one-time pad, then you can provably not really do any better than this. It's as strong as it gets. And the whole process is symmetric. So what you need to do is get some other students to take the encrypted text and the key, reverse the whole thing, and they should get the same message out. And usually they do it, and the nice thing is if they get 1 or 2 letters wrong, it doesn't really matter, the message comes through. So we've just learned about a whole bunch of other stuff. We've learned about pseudo-random numbers. The way computers normally generate numbers is through pseudo-random numbers that look sort of random, but they're not really. We learned about some probability, binary arithmetic, logic gates, so exclusive OR is a nice logic function, and encoding text. All of these things sort of fundamental aspects of computing. So if this encryption process with exclusive OR using a one-time pad is so perfect, why are thousands of mathematicians still employed? Why does the NSA still exist? So all we've done is we've reduced the problem of doing encryption to the problem of how do we get this key, this one-time pad, how do we distribute this to the other person? So I'm Alice. I've created my key, and Bob wants to decrypt the message that I've encrypted with this key. Bob has to have the same key. So I have to pay someone with a briefcase and handcuffed to them to take my super secure key and hope that no one intercepts that on the way. And because I can only use the key once, this is a very expensive process. So you can imagine creating a DVD full of ones and zeros, a key, and you can use little bits of that at a time. And if you want to be super secure, there might be people that really do that. So in practice, what we do in the real world is we don't use symmetrical algorithms. We use asymmetrical algorithms. We use algorithms like HTTPS and SSL, which you would have heard of. And the way these work is that I can publish a key that allows you to encrypt a message to send to me, but I have the private information needed to decrypt it. So these algorithms work great in practice, but they're actually quite expensive. There is, however, a much sexier way to distribute a one-time pad than to get a guy with a briefcase. I can use quantum cryptography. Now, can you imagine teaching your students quantum cryptography? I mean, this sounds like the kind of thing that should be an advanced university course. Now, I'm not going to do it with you today, but my claim is that an A-level class should be able to get the basic idea of what's called the BB84 quantum key distribution algorithm. And all you need is 2 pairs of polarizing filters and a light source. So you can get polarizing filters. I've done this before. Right? I got all these old laptops, ripped them open, take out the screens which are polarizing filters. These are linear. You get some circular polarizers. So if you have 2 pairs of these, you can actually set up this entire experiment in the classroom. Right. So I don't want to go too much into that right now. Yes, it is hard, but that's sort of the point. So what is all about? I mean, it's nice to learn about encryption and stuff, but what is my point from a pedagogical point of view? I picked three real-life stories today. We've just done the first one, encryption, that are, they have both a human element, have a story behind them, but they're also difficult. And my belief is that you can take any of these technologies and really break them down to a point where students can understand them, and because they're real and because they have a story behind them, they have a lot of motivational power. So I think physics and mathematics, they know this trick. When you learn about mathematics, you learn about Euclid, you learn about all of these people through history that have contributed to mathematics. When you learn about physics, you learn about Einstein. They're sort of intertwined. The history of science is often intertwined with learning about science. And somehow, to me, in computer science, in computing, we don't do this. We're so tied up with the glory of the technology, you know, the wonder of sprites moving around and things going, machines that go ping, that we sort of forget to tell this story, which is a very motivating thing for students, I think. I also think we should dive deep. We shouldn't be afraid of really digging into the technology, like quantum cryptography. It's very, very complicated, but it is actually achievable to get students to understand this. So Steve Ferber said something very interesting this morning to me, said it to all of us. Paraphrasing, he said something like, he thought he had a better learning experience with punch cards than students get today. And this really rang true to me because, well, let me take a step back. I think computers can only do three things. So they're actually fairly simple devices. They can move data in and out of registers. That's one. They can do simple computations, simple mathematical computations, transformations on this data. And the third is that they can change their execution path based on simple comparisons or external interrupts. So maybe you could argue with me about that. And you're right, actually. Computers can only do one thing. They can take a set of bits, and they can turn them into another set of bits. That's the bottom line. So all of these programming languages that we create are abstractions to help us create complex programs rather than just typing assembler all the time. These abstractions are necessary. So these different programming languages from C to Python, to things like graphical programming languages, they're all necessary abstractions, but there is a slight risk that we can abstract so far that we lose touch with the hardware and the joy of knowing exactly what's happening in the machine. It's very empowering to know that when you are writing a little bit of code, that it's going to be transformed into these very simple primitive operations. Okay. So whenever I get overwhelmed by the complexity of some piece of technology, I like to remind myself of this, and somehow I find it coming. I mean, when I wrote my first Pascal program and compiled it, I was like, wow, this is compiled. This is the real thing. This is the machine code. This is running on the processor. It's hard to get that sort of sense sometimes when you're writing, say, Java code for a virtual machine. Right, so, and I appreciate most of you have a syllabus to follow, but I hope I'm arguing that most of the stories that you can tell in this area can be used to teach the fundamentals. Incidentally, this picture is a real-life Turing machine that someone's built. So it has plastic tape, and here's a wheel that can erase ones and zeros, and here's a pen that can write them, and the rest is in solid-state logic. I'd really love to build one of these. That'd be cool. Look great on my desk. Okay, so one last point. All of these stories demonstrate the immense impact of the technology. Things like the Enigma Machine. The Enigma Machine is not just about mathematics. It's not just about doing things faster. It's sort of a story that illustrates information theory at its purest and at the same time most practical. So they're very, very powerful stories. All right, so we did the Enigma Machine and the history of encryption. Let's talk about two other stories in the remaining time if I get through them. Here are my bosses, Larry and Sergey. And here's one of the first Google servers that they ever built. And yes, the case is made out of Lego. And this is actually sort of reminding me of just the color scheme. You can see where the Google color scheme comes from now. But this is somehow reminding me of the Scratch system that we've learned so much about today already. So back in 1998, when the Google search engine came out, what is the thing that made it different? Can anyone tell me what sort of accurate results? Why were the results accurate? Sorry, someone said PageRank. Right. So PageRank is a way to analyze the links of the web in order to figure out which pages are the most popular. So there's lots of mathematical ways to describe this. You can talk about it in terms of linear equations, solving a linear system, inverting a giant matrix the size of the web. You can talk about it in terms of graph theory, drawing nodes and links and analyzing the backlinks. You can also talk about it in terms of random algorithms. And that's what I'd like to do today. So I've rewritten the web for the purposes of this session. So it's posted up around the room from A to J. So we have 10 web pages. And I'd like some volunteers to come down and perform the PageRank algorithm. So I have dice here, so I need 30 volunteers to take a die each. And I'd like to suggest that the front rows, it would be just easier if the front rows stand up. And just to start with, just come down the front, grab a die, and just move to one of the pages, distribute yourselves randomly amongst the pages. So on each page, please start coming down, and I'll keep describing. Maybe I'll wait till people have randomly allocated themselves. So again, I've done this in the classroom, and it really strongly illustrates the way the PageRank algorithm works. So this is the random surfer model of PageRank. So each page has got 6 links, 6 numbered links. So the people standing around throw the die, get a number, and read the links on your page, and it will be mapped to a letter from A to J. So when you get that letter, walk to the page that it points to. So you're following the links, in other words. So start that process now, and I'll let you walk for a couple of minutes. There in front. Keep going. Keep going. I really hope this is going to work. There is a finite probability that it doesn't. Okay, can you stop at the next page? Okay, maybe, okay. All right, we done? All stopped? Okay, good. So we've just performed the PageRank algorithm. So the page with the most people, looks like J over there, is the most popular page on the internet. Page, what's that page? E? Is the next most popular page by the looks of it. So bear in mind that we haven't done any search query yet. All we've done is establish an overall ranking of the web pages. So now I do a search. Let me search for the term vampire. So everyone, please have a look at your web page, and if you can see that the web page is about vampires, put your hands up. All right. So these pages are about vampires, but because this page has got the most people on it, the highest page rank, I declare this as the first page. Now, of course, I predicted way ahead of time that this was going to be the case. Because we actually, when we designed this web, we did the analysis, and we produced the PageRank using the real algorithm before we came here. So let's do it again. If I want to search for werewolves, put your hands up if your page looks like it's about werewolves. Okay, again, page J wins, and we predicted this ahead of time. So the number of stars is kind of like the PageRank. Thank you, everyone. So PageRank was supposed to be this wonderful, complicated algorithm. It's got lots of papers. That's it. And actually, because the web is so big, this is not so far divorced from how it's actually computed in real life. Obviously simulated.
Can I ask a
Yeah.
Are you talking about how many people visit the page in the Google Apps, or how many other pages point to that page in the Google Apps?
It's essentially how many other pages point to that page, but it's not a single link, right? It's how many pages point to those pages, and it's all a cyclic graph. So another mathematical way to think about this is you sort of pretend it's a graph. You can do Monte Carlo algorithms on it, and you can establish this kind of standing distribution of visitors to a page, and that's sort of like the PageRank. Okay. So we've learned now about the internet, we've learned about the World Wide Web, we've learned about HTML, we've learned about graphs, graph theory. We may have thrown some linear algebra in there because you can compute this by solving a set of linear equations, 10 linear equations in this case. And we've learned a bit about random algorithms. And there are some search factoids up here as well. So PageRank is one of only 200 plus signals these days in the Google search ranking. There are more than 1 billion search queries per day. And if you kind of compute that per second, it's something like 17,000 queries per second. This is one of the big differences between students at university doing computing and students coming to Google to work, is that like they have difficulty grasping the scale at which these things work. The average response time for a search is less than 250 milliseconds, and I think by comparison, blinking your eye is something like a tenth of a second. And there's over 1,000 person user development in trying to get the ranking as good as possible. And I like the last one, even though it's not really search related. We get 35 hours of video uploaded per minute to YouTube. A lot of people with too much time on their hands. Okay, so the next thing I want to talk about, the third story, is Hawkeye sports technology. So how many of you are familiar with Hawkeye or seen the results of it, right? And as far as I know, it's a British company, or at least it was definitely developed in Britain. So it's a fantastic story, especially around about now with Wimbledon going on. So it's the same company, same kind of technology that does the tennis stuff and can even do football. So how does this work? I mean, it looks really amazing when you see it in real life. How can they know that Shane Warne, sorry, I'm Australian, Shane Warne's the only spinner I know right now. How can they watch the way he bowls and figure out that it's going to land and it's skidded off that way and it would or would not have been an LBW? So there are three problems to solve here, and they can all be broken down. They're all interesting problems in their own right. The first one is, obviously there are lots of cameras watching the action, and they're high-speed cameras. They're very cool technical devices in themselves. But at the end of the day, we get an image from them, and the image is still often very blurred. So how can we figure out where the cricket ball is in this image, or whatever other ball is in this image? The first trick that we can do is we have a fixed background. These cameras aren't moving, so we subtract off the background. So because the ball is the only thing that changes from frame to frame, the ball is the only thing that shows up. Actually, there'll be a batsman in there, so the batsman confuses things a great deal. But you can see immediately that this is now a much easier problem to find a round object. So I can detect that the ball is in this frame. I can do this over a sequence of frames. So I might have 10 cameras all pointing at the stumps, and they produce something like 60 frames per second or 100 frames per second, and I can pick out the ball from each one. So this is already a fantastic start. So the second problem we have to solve is, given that we have multiple images of a ball taken at the same time, and we've located the ball, how do we turn those 2D images into a three-dimensional picture of where the ball is at that moment in time? So I also have an exercise, so I need 2 volunteers to help me with this one. Thank you. And one more volunteer. Thanks. So you guys are now cameras, your high-speed cameras, your very expensive pieces of equipment. You're on the left, and you're on the right. So you can stand about about here. If you could stand about here. So there are your stumps. Okay. So you need to sort of imagine that your eye is the center of focus, and it might actually help to close one eye to do this. Doesn't matter which one. And the transparency here is the plane of the camera. That's the image that we've taken. And what's happened is that when we've taken this image, the ball is somewhere around here, and a ray of light has traveled from the ball back to the focal point of the camera, creating a shape on the image. And what happens in the computer when we're actually doing the stereo reconstruction is that we're sort of reversing this process. And I'm going to try and simulate this with two laser pointers. So the laser pointers represent the rays of light. So this cutout is where the ball is on your image, and you've got another cutout in a slightly different place. So if you could try and take one hand, and there's the button, and try and shine it through the image at the corresponding point there, and here's a... Does this work? Yes, you do. Okay, so that's where the ball would be for you, and just shine it through to roughly where you think it should go. Just there. All right. So now what I do is I'm going to try and find the point in space where these two lines most closely intersect. So I'm just doing this bit by trial and error, but obviously you can do some nice linear algebra to figure this out exactly. And they were closer together, but I think my helpers are getting tired. Right. So I'm going to say right about here is where the ball is. So we're done. Imagine, of course, thanks guys, that there are actually 10 cameras, and they're a little bit less shaky than my helpers. So the system is actually accurate to within the radius of the ball itself, which is what you need. Great. Okay, so we solved the first two problems. We have the third problem to go. Actually, so we have a sequence of frames in time, and we've actually, from each of those frames, we've figured out a point in 3D space where the ball is. So now, how do we model the trajectory, the flight path of the ball? So this is where there's a fantastic link back to Year 10 mathematics. It's just a quadratic equation. If you want to simplify it, it's just a quadratic equation. So I have all of these points in time, and I just have to find a quadratic equation that fits here. Now this is actually interesting from a high school point of view, because in high school, like, you learn, well, I only really need 3 points to figure out a quadratic equation. Well, here there are more, and this is a problem because they're not all going to agree. So you have to sort of deal with a little bit of noise, find the best fit that you can. And then when you start getting more sophisticated, you can start thinking about spin. You can start thinking about how the ball shifts in flight. And once you've got that, you can actually also continue to predict the bounce, and you can actually figure out if this would have been an LBW decision or not. So we're done. Of course, this happens in almost real time at the cricket or at the tennis. So there's an awful lot of technology, an awful lot of glue, which is bringing that together and sending out a broadcast signal. So I said that I wanted all of these things to have a story. So what is actually the story behind Hawkeye? Well, for me, this is a very personal one, because when I was an honours student at university, I got to build with a friend of mine a prototype system of Hawkeye before anyone had ever heard of Hawkeye. So this is the Ashes Tests 1998 Boxing Day. So I'm here with my mate, and we have our prototype system, which we're demonstrating to the broadcasters, Channel 9 in Australia, and they thought this was like the best thing ever. I mean, they hadn't really thought about the possibility of this technology. So this was this was the accumulation of a year of hard work for us, and we spent a year in this lab, and we had this box, and we had this tennis ball, and we had this this set of wickets, and we spent hours and hours and hours bouncing tennis balls that had been soaked with water so that when they hit the calibration box, we could sort of figure out from the splotch of water where it really landed and seeing how accurate we could get it. So I'd love to say that I made $1 million out of this and we sold it to Hawkeye. That didn't happen. Hawkeye were working on this stuff independently. The best that we can say is probably that we busted some patents. Anyway, so we've just learned about image processing, stereo vision, 3D graphics, quadratic equations, all pretty sexy things. So to finish off with, these aren't 3 isolated examples. There are lots of different fantastic stories out there that you can tell your students. The Sinclair Zx Spectrum is another great British story. And again, for me, actually I grew up in the UK, and this was my first computer. And I'm sure for many of you, you had Sinclair Zx Spectrums and you cut your teeth on these, as I did. So when I got my first computer, my first one of these at age 7, my mum and dad started it up and they started going through this demo program and they got stuck. They couldn't get it to do anything. So they left and I had to go and I just went bang, 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 and it worked. I'm like, this rocks. It's fantastic. So games are another, I mean, we've spoken so much about games today, but when you look deep into stories like ID Software that developed Wolfenstein and Doom and Quake, there are actually sort of good stories behind there. Will Wright, who developed The Sims and Spore and stuff like that, starting off with SimCity, which was a fantastic game. A lot of good technology, very innovative. The first coders, so I had to add Euclid in here. So that's why there's a punctuation mistake. Robotics. So again, I think it was a Polish author who really kind of coined this idea of robotics back in the 1920s, maybe. Czech. Sorry, thank you. Isaac Asimov and his laws of robotics. And again, football. How many of you have seen the RoboCup stuff? They used to have the little robotic dogs. Now they've got kind of bipedal robots. So it's actually amazing to watch this and look at some of the technology behind it. I wish I had this, but I have some vision from some of these dogs, some of these robots as they're playing soccer, and it's all over the place. You can't imagine how they can actually figure out where the football is to kick. Synthesized music is also a great story, so there's a lot of history behind that and development of synthesizers. Of course, Alan Turing, the award and the test, another good story. The first computers. More modern stories, self-driving cars. So there was this competition to build a car that could drive itself across the desert. And the first competition, it was DARPA Grand Challenge. The first one was a dismal failure. Nobody really knows about that first version. Like, I think the best car got 20 miles or something before it gave up, fell in a ditch. But then they actually managed to, I think it was Carnegie Mellon at the time, they managed to create a car that could drive around an open track completely by itself, and it won the competition. Then the following competition was in a closed environment in a sort of a city space. And now there are cars driving around in California completely automatically with a driver there in case something goes wrong. But this is happening, this is real. And a personal story for me, because my background is in artificial intelligence and machine learning, the first time I was really, really impressed by this idea of artificial intelligence was when I heard the story of Gary Saro, who taught a machine to play backgammon. And he didn't teach it in the classical machine learning way, which is to present a bunch of board positions and a good move. He taught it in a method that's called reinforcement learning. I mean, it's not unlike Pavlov's dogs. You give the machine a reward when it does the right thing. You give the machine a virtual reward for winning the game and a virtual penalty for losing the game. And by playing itself with this very, very weak signal, it learned to play backgammon to a grandmaster level. And he played it against human players. And the amazing thing was that the human players said that they picked up strategies that they had never thought of before that made sense, but they'd just never seen them before. And it was because we didn't bias them with the human way of playing. They really taught themselves from scratch. And the same person was involved in the Watson computer with IBM that won the Jeopardy challenge. So my final message is, please use these amazing stories, all the amazing stories that you can think of, to help uncover the fundamentals of computer science. So just today, Scratch, Connect, smartphones were things that I learned about, stories that I have discovered that I think are fantastic stories. And hopefully by doing this, we can educate the next generation of engineers. Thank you.